Hey, let's talk about what you need to know about imaginary numbers and complex numbers. Remember that complex numbers and imaginary numbers are just one more set of how we can organize the universe. And we talked about natural numbers, whole numbers, integers, rationals, real numbers, and that imaginaries are anything outside of that. But what does that mean exactly? So for a while, the square root of -1 has had no solution. There's nothing you can there's no way to square -1 and get something that you can then take the square root of and get back to -1. And so you've been taught for ages that that's it, that's the answer, deal with it. There's no answer to the square root of -1. Turns out a bunch of people for a long time have been thinking about, well, what if there was? Well, and so they've kind of been thinking about this since 665 AD, so quite a long time. And it turns out we can actually use this in different kinds of math and in video game production and differential equations and physics and fancy schmancy things. But all you need to know is how to solve some very simple solutions using imaginary numbers. So, what am I talking about? So if we say, here's a rule, the square root of -1, we're just going to call it I for imaginary, because why not? Sounds great, sounds awesome. So that's what people did. They said, okay, we're just going to create this rule, everyone needs to deal with it, the square root of -1 is called I. So then what we can do is we can say, all right, what happens if we square both sides of this? Well, that means I squared, if you take the square root of something and you square it, you just get rid of that square root and it becomes whatever's under it. So I squared is defined as being -1, and that's another rule. Don't worry too much about where it came from. There's a bunch of Greeks and it's not just dead white guys who thought about this. There's actually some very old, those people who started thinking about it in 665 AD or whatever I'm actually supposed to call it, not AD. The first people to think about were from India. They were Indian mathematicians. And so it's not just dead white guys, but it is just dead guys who were thinking about this at first. But anyway, the rule is the square root of -1 is I. So basically what we're saying is anytime you see a square root that has a negative under it, take that out and call it I. Or just square it, and then all of a sudden, this I squared is defined as being -1. So now, traditionally, math teachers want you to learn the first 4 powers of I, okay? So I is the square root of -1, or you could say the square root of -1 is I squared is just -1, okay? That means that I to the third, well, that's just I times I squared, so it's -I is what it comes down to, -I. Okay, because if you think about it, and this is just kind of the rule, if you're worried about where did that come from, well, we have that negative number here, we have that negative here, and we have an I here. If we do I times I squared, that gives us -I. Sounds awesome. Well, then what if I have, instead of that, I have I to the fourth? Well, that's just I squared times I squared. -1 times -1 is just 1, okay? I don't like to think that hard about. So the idea is that most teachers are going to tell you, memorize these 4 things. I is a square root of -1. I squared is -1. I to the third, I cubed is -I, and I to the fourth is 1. Okay. I don't like thinking about I to the third or I to the fourth. I just like thinking about I and I squared, and as long as you do that, you'll be okay. So in class, I think I confused you a little bit talking about these powers of I. Forget all that stuff. I'm going to teach you, don't forget it. It is actually good stuff. And if you understand it, that's awesome. But I think I confused a lot of people with it, so we're going to skip right over it and go straight to the kind of problems you're going to see on the SAT, on the ACT, and very importantly, on my test, which you would like to be prepared for, I'm sure. So the kinds of things you need to make sure you understand for this class and the future of your math career, because this will become very important in pre-calculus and especially in calculus, is that anytime you see a negative sign under the square root function, this is no longer an irrelevant function. It's no longer something you can just say, oh, there's no solution, I'm done with this problem. What you have to do instead is take out that square root. So when you see that square root there, the first thing you think of is, hey, I'm actually going to take that out and I'm just going to call it I, and then I'm going to leave whatever else is under there, okay? So the square root of -5 is actually I, and then root 5. We can't simplify root 5 anymore. Okay, so let's try that again here. So, oh no, there's a negative number under the square root. I'm going to immediately call that I and bring it out. So negative I times the square root of 7. I can't do anything else with that, so I'm done. And here we go. Oh no, negative under the square root. Can't deal with that. Hurts my brain. I'm going to take that out. I'm going to call it I. And then we have root 99. But wait, we can do more here. So 99 is the same thing as saying, so don't forget your I. So there's my I. 33. No, I don't want to do that. I want to do 3 times 11. No, I don't. I want to do 9 times 11. 3 times 3 times 11. That's what I'm thinking. Times 11. All right, well, here's a lovely square pair. I can take that out, okay? So then your final answer is going to be I, and then there's a 3 pulled out, root 11. So that's your answer to that one. So anytime you see I outside of the square root, that means, oh, hey, originally that was a negative root, but we've already taken care of it. It's done. All right, so what happens when I multiply something that has an I attached to it, which means it was originally, there's some square root of negative 1 going on there, and I converted that square root of negative 1 into an I. Well, in this case, you just treat it like a variable, like it's X, like it's Y, like it's G, whatever you want it to be, but and then you see what happens at the end. So in this case, we do 47 times 2, and then we have I tacked on to the end of it, so it's 47 times 2 times I. Okay, so that is 94. There's my equal sign, 94 I. All right, so we can't do anything else. 94 I. 94 is an integer. I is just I. We're done. That's a proper way to do it. Now you might think, well, what if instead I make this 94 root times the root of negative 1? You would be right, but you're not accurate. We like to leave it in this form where, first of all, I is easier to write than the square root of negative 1, so everybody's in math is lazy. Well, no, they just like to be efficient, and this is much more efficient. So this is a proper way to deal with the square root of negative 1 now. So let's go on to the next one. It's 2I times the root of, oh no, I have a negative sign under a root. I'm not okay with that. I need to immediately take that out as an I. So much better. So now I have 2I times the root of 5. Okay, cool. I'm going to combine, not combine like just, I'm going to multiply these just like they were variables. If this was 2x times x root 5, you'd get 2x squared root 5. Same thing if it's an I, but we're going to go one step further at the end. So this becomes 2I squared. Ooh, that looks like a cube. It's supposed to be, there we go. So I squared root 5. Well, we know something special about I squared. So I squared equals negative 1. So you can actually replace, anytime you see I squared, immediately replace it with negative 1. Okay, that's just how we roll now. That's just the new normal is that if you see I squared, it's actually negative 1. So 2 times negative 1 is actually negative 2. And then we still have that root 5 hanging out. So the final answer is negative 2 root 5. We can't simplify this any further. We're done. Problem solved. Okay, so this next one, we have a negative sign, and then we have times the root of negative 3. Not okay. Let's take that out as an I. And when that times the root of negative 7, again, not okay. I'm going to take that out as an I. So let's rewrite this so it's neater. We have negative I root 3 times I root 7. So don't get confused just because there's a negative sign in front. Obviously this problem is trying to keep you confused by putting it there, but that it has actually no bearing on the I at all. It just is to keep in mind at the end of the problem. Okay, so let's multiply these out. We can multiply our variables. Okay, so I times I, we're going to keep that negative sign in front. We have I squared, and if we have these roots, we can combine them under the root, and we get root 21. Oh, but look, there's that I squared. I squared we can immediately replace with negative 1. So we get a negative 1 times the root of 21. Awesome, negative is positive, // and we get the final answer here is the root of 21. We can't simplify that any further. That's all there is to it. Okay, a complex number sounds very, very fancy, but just like the imaginary numbers, it's less fancy than you actually think it's going to be when you actually get to it. A complex number is just when you have some real number, okay, 5, 83, negative 47, whatever you want it to be. It could even be a decimal or a fraction or anything, any real number, plus some imaginary number, and it could be multiplied by any other real number, okay? That's it. That's all it means, okay? So it's like -4 plus 3i, or 157 minus 83 halves I. Doesn't matter. If you have some real number and then some imaginary number, that's a complex number. That's all there is to it. It does add just like a variable. It multiplies just like a variable. The only places it gets strange is when you think absolute values and graphing, and we're going to talk about that. Okay, so let's add these. 7i plus 9i. Treat this just as if they were x's, okay? So if this were 7x plus 9x, you would say, oh, that's 16x. Well, same thing here. It's just 16i. We can't go any further with this. It's not an I squared. We're done. Okay, so in this case, in number 13, so that's done. Good job. Okay, so now in number 13, they've added these parentheses around the two complex numbers because why not? Just to confuse you. There's no reason to have them in this case because we're adding, not subtracting, dividing, or multiplying, so that doesn't actually matter. Which, I mean, the parentheses don't matter. So let's go ahead and add these. We're going to combine some like terms. Okay, so we know that we've got the -5 and the 2 are going to combine to give you -3. We have the 6i and the -11i to combine to give you -5i. And you're done. That's your complex number, okay? Easy peasy lemon squeezy. Check it off your list. Okay, so here in this next problem, the parentheses do matter because we have a negative sign separating our two complex numbers, just like when you have any other situation with division, or sorry, with parentheses. But like normal, we're just going to combine our like terms. But in this case, it's a -4. So let's go ahead and write this out first. So the first set of parentheses doesn't change, but then we get a -4 and a -2i. Okay, so that's changed. So we have 2 and -4, so -2. And then we have 3i minus 2i is a positive I. So that is our final answer there. Okay, let's see a couple more examples here. We have 3i times 4i, so we're going to deal with this just as if it was 3x times 4x. Multiply your integers first, and you get 12. Then multiply your i's, and if this were x times x, it would be x squared, but it's I times I, so it's I squared. But wait, we know that I squared is actually -1. So this is actually going to be 12 times -1, or -12, okay? So same thing if you have this parentheses here. Remember, you have to distribute that square to both, okay? So the integer and the x, or sorry, not exponent, the variable in this case, which is I. Remember in these situations, what I see the most is people ignore the integer, and they'll put 7i squared and then move on. No, it's 49i squared. But then remember, again, I squared is -1, so this becomes -49. So gross. What if we are multiplying two complex numbers? We treat this just like foiling, and I know foiling is a bad word sometimes, but it's actually pretty easy. And it actually has a fun twist at the end, which we love. In math, it's an easy twist. So foiling, remember, it's first, okay? So first times first, 4 times 7, 28, okay? And then outside, so 4 times 2i, so plus 8i, and then inside. Okay, so plus 21i, and then last times last, 3i times 2i, so plus 6i squared. Okay, so there's a couple things we need to do to finish this out. Okay, we need to combine our like terms. Okay, so this is actually now 28 plus 29i. And, oh, look at this. This is actually so I squared. Remember, as soon as you see I squared, you immediately say, that's -1. So this is now minus 6, because it's going to be 6 times -1. Well, look, now we have two new like terms to deal with. So 28 minus 6, 22 plus 29. I is your final answer. And look at that, we're back to another complex number. We have a real number and an imaginary number. So when you FOIL two complex numbers, you end up with another complex number. So what if you're dividing complex numbers? If you're dividing one real number plus an imaginary number by another real number and a complex number, what happens? Well, the rule is you can't have a imaginary number on the bottom. So we're going to create a difference of squares is what we're going to do, because we saw in the last one, when you FOIL two complex numbers, you get rid of you end up with an I squared, right, which is a negative negative 1. And so what you can do is actually deal with this so that you get rid of I altogether by thinking about difference of squares. So if I did this complex number is 1 minus I. If I then multiply it 1 plus I, magic will happen. Just trust me on this, okay? You're gonna see what happens. But whatever I do in a fraction, in order to retain equality, I need to do to the top as well. So I need to multiply the top by 1 plus I as well, okay? So let's see what happens. I'm gonna FOIL the top. So this becomes negative 5 times 1. So again, negative 5. Negative 5 times I, so plus negative 5I. And then 9 times 1 plus 9I, and then 9I times I plus 9I squared, okay? And then I'm going to keep that for right now, and then we'll come back to it. I'm going to do then the bottom is 1 times 1, 1 times I, so plus I, negative I times 1, minus I, and negative I times I, so that's negative I squared. Okay, so the first thing we see is that these two go away. That's what happens when you have a difference of squares. You end up with no middle variable, right? And so those go away, and you end up with the bottom here is going to be the denominator will be 1 minus I squared. Hey, I squared. I know that it's negative 1. So this becomes 1 minus negative 1, or 1 plus 1, or 2. So right now my denominator is sitting at 2. So let's simplify the top now. Let's go back up to the top. What do we have? We have these two numbers that can combine. So right now we have negative 5 plus 4I plus 9I squared. Oh, wait. I squared, I can get rid of that and replace it with a negative 1. So this is actually minus 9. Awesome. I can now combine that negative 5 and that negative 9. It's give me negative 14 plus 4I. Whoops, that's not an I at all, is it? Dun, 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 plus 4, 4I. There we go. And then remember that that's all over 2. And you would be done, except that you can simplify this fraction even further. So I'm going to divide everything by this 2 to get rid of that. So negative 14 divided by 2 is negative 7. So that's this. And then 4I divided by 2 is just 2I. So 2I. And you're done. That is your final answer. So the way you do these division problems is you always go back and you multiply the whatever's in the denominator by whatever will make it a perfect square. So if this was 87 plus I, it's going to be 87 minus I on the top and the bottom. And then you just FOIL those out and you're done. So you might be saying, can you just do one more, maybe for fun? It's not that I don't get it. I just know you love doing math, Miss Noel. And of course, I will oblige. I would love to. So here we go. We have two complex numbers being divided. I can't have any i's in my denominator. So what I'm going to do is I'm going to multiply both the denominator and the numerator by what makes the denominator a difference of squares, okay? So all that means is I do the same thing, same complex number, but with the opposite sign, okay? So it's going to be 3 minus 5i, and then I have to do the same thing to the top, 3 minus 5i. Awesome, and then it's all just a foiling game, okay? So then I get, 2 times 3, 6, 2 times negative 5 is negative 10i, and then I have negative 3 times 3, negative 9i, and then negative 3 times negative 5 plus 15i squared. Awesome. There is my numerator. I'm not going to simplify it yet, even though I'm really itching to. I'm going to do the denominator first, just so I don't forget any weird steps or anything. Okay, so same idea, we're foiling. Okay, so 3 times 3 is 9. 3 times negative 5 is negative 15. Oh, but there's an I, so it's negative 15i. 5 times 3 is positive 15i. Interesting. And then 5i times negative 5i is a negative 25i squared. That's a 5. Okay, so let's see what we can do to simplify all this. Totally didn't just drop my iPad. Everything's great. Okay, so look at this. We have an I squared. We have an I squared. Anytime I see I squared, I can immediately replace that with a -1. Boom. So I'm going to put a negative sign in front of that 15. That, and then the I squared is gone. Again, I squared, I'd put a negative sign in front. There already is a negative sign in front. So I'm actually just going to make it positive. So that's step 1. Step 2 is we're gonna combine like terms. So we have this like term and this like term on the numerator side. On the bottom, we have -15i and +15i. So those two just cancel each other out. Okay, so what does that leave us with? Let's write it again. We have 6. We combine some like terms. -19i squared minus 15. Huh, interesting. In the denominator, we have 9 plus 25. So we still have more like terms we can combine. We have some integers we can combine. We have this 6 and this -15. So we have -9 minus 19i divided by, and then 9 plus 25, 34. We can't divide this any further because 19 is prime, so that makes this your answer. So hopefully this is a little bit more clear. Whenever you have a complex number in your denominator, you have to multiply by what makes it a difference of squares. And what I mean by that is just if you have a plus sign here, multiply by the same thing, but with a minus sign. And reverse, if you have a minus sign, you use a plus sign. And whenever you do to the denominator, you have to make sure you do to the numerator as well. Then you just simplify. So I know what you're thinking. Hey, how do I graph an imaginary number? I know this like hurts you when you want to go to sleep, but you're like, but wait, I don't know how to graph imaginary numbers and I really want to know. It's so exciting. Okay, maybe that's not what you think about before you go to sleep, but somebody did because they figured it out. And what they did is they decided, all right, imaginary numbers kind of follow their own rules, so we're going to give them their own axes. And so the x-axis instead becomes the real axis, the y-axis becomes the imaginary axis. So if we were going to find a point on the imaginary plane, or a complex number on the imaginary/real plane, what you do is you find the point. So let's say we're looking for C. And we're like, hey, C, what's your complex number? Well, if you were to find this point as, if you were to find this point as a regular point, it would be 2, 1, right? Because that would be your x value and that would be your y value. Well, in the world of imaginary numbers, what's really happening is the x is the real number and the y is the imaginary number. Okay, so all that means is this becomes 2 plus, what is that, a 1? So just I. That's it. C is just the complex number 2 plus I. Seriously, that's all it is. Ridiculous, okay? Let's make up a point. I'm going to make up a point here. If this is our point, okay, if I were to do this as a real number, or as a real point, it would be 3, -3. But in the world of complex numbers, this is 3 minus 3i. That's it. Seriously. Don't question it. There's rules. It has to do with coding, it has to do with the electromagnetic plane and the right-hand rule and other things. Just roll with it. This is what you need to know to be successful in Algebra 2 and pre-calculus. Once you get to, like, 3rd year calculus in college, if you get that far, then you start to talk about it in more detail. For now, just know that that's what this is, okay? So we talked about squaring numbers, talked about multiplying these numbers. What if you're asked to find the absolute value of these numbers? And you may say, I'm never asked to find the absolute value of these numbers. Well, but just kidding, you are in this case. And here's how you do it. Whenever you are finding a point on a line, or on a plane, what you're really doing is you're finding its distance from the origin, okay? So this point that we made up here, its distance from the origin is 3 minus 3i, okay? That is what we've defined it to be. So if we want to know the absolute value, what we do is we create a triangle. And we say, okay, it is -3 in this direction, 3 in this direction. If I want to know the absolute value of this, I basically just treat this like the Pythagorean theorem. So the absolute value of this number equals C. Okay, that's what we're going to call it in our Pythagorean theorem. If we say that a squared plus b squared equals c squared in our triangle, well, the absolute value is c, okay? So what you do is if you're trying to figure this out, you just say, okay, if I were trying to find c by itself, I would take the square root of both sides. Boop, okay? And so that means for this number specifically, it would be the square root of 3 squared plus -3 squared The I does not come into it at all. I know that's confusing. Don't think about it. Don't worry about it, because what we're thinking about actually in this case is this distance and this distance, okay? And that's going to equal C, or the absolute value. So this becomes the square root of 9 plus 9, or 18. And we can actually simplify that because that is 2 times 9. 9 is a square root, so okay, let's do it this way. 2 times 3 times 3. There's a square pair, can pull it out. So 3 root 2 is the absolute value of this function. Okay, so let's do another example. So let's look at this. If I'm trying to find the absolute value, if I were to ask you to find, if I had asked you to find this point, you would have given me it's 3 plus 4i, because that is where the point is. It's 3 comma 4, but in this universe of imaginary numbers, it's 3 plus 4i. So if I was just giving you the complex number 3 plus 4i, and I didn't give you anything else, you would still be able to tell me what the absolute value is, because what that is, it's just the, the square root of the real number, 3 squared, plus the coefficient of the imaginary number squared, so 4 squared, okay? So that's 9 plus 16, square root of 9 plus 16, or 25, becomes 5. That is the absolute value of this complex number. That's it. It looks crazy complicated, but that's it. It's ridiculous. And now you know everything you need to know about imaginary numbers to be successful in Algebra 2. So you may be saying, but seriously though, what is this ever used? Again, this is used in the higher maths, like differential equations, which is basically third-year calculus. We're going to talk about it when we talk about solutions in polynomials, when we get into complex quadratics. Physicists use this when we're talking about electromagnetism and when we're dealing with electronics. And it's actually kind of interesting how they deal with that, but that's beyond the scope of this course. We can talk about it independently if you want. Which means if those are how you can use complex numbers, the people who do this are engineers, physicists, and mathematicians, and anyone who uses differential equations, which is actually more than you might think, and an incredibly lucrative field, especially for women in the mathematics. So I encourage people to look into it. So hopefully this all helps, and let me know if you have any questions.